So imagine the following problem. We've got the bounded region between the graph of f of x equals x minus 1 squared plus 1 and g of x equals 2, and you already know what's going to happen. You already know what's going to happen. I'm going to come in and I'm going to draw a graph of this region once again. And this is where it really becomes advantageous, to have gone thoroughly through pre-calculus and learned how to graph all of these functions by hand quickly. Here is g of x equals 2, that constant function, and here is f of x equals x minus 1 squared plus 1. Now, we're going to take this region and we are going to spin it around the y-axis. We're going to spin it around the y-axis, and that's the solid that we're going to form. So I think it will look a little bit like a bundt cake if we do that. The question is, what is the volume, I should say, of the solid that we form if we spin around the y-axis? Now, previous videos, we discussed this issue where if you're going to use the formula for the method of washers to calculate the volume of this solid, you absolutely need to make sure that the independent variables of your function is a match to the variable of the axis that you're spinning around. So I could, in theory, go through and take f of x and find its inverse and do all kinds of calculations in such a manner. But perhaps I would be able to find this volume in a different way if I just thought about taking the cross sections in a different manner. So I'm going to sketch this solid of revolution, but I'm going to do it in a slightly different way than I've done it in the past. I am not going to fill up this region using horizontal slices that look like discs. I'm going to start by taking a vertical line at some arbitrary x value in this region, and I'm going to draw the vertical line segment from top function to bottom function. And I'm going to spin this vertical line segment around. I'm going to spin this vertical line segment around, and as a result of spinning that not horizontal line segment, but spinning a vertical line segment around, I have acquired a cross section that looks like a cylinder. So I am still taking cross sections of this volume, but I'm not taking them with a bread knife this time. I'm taking them with a cookie cutter in some sense. I am taking cylindrical cookie cutter cross slices out of this solid of revolution. And so I'm going to try to add up the surface area of each of these cylindrical cross sections. So here's our idea. Integrate the surface area of cylindrical cross sections from the starting x value, the innermost x value, to the final x value, which I think if I recall correctly from our previous video, we found that this was located at x equals 2. Now, I had a student put it this way, and I thought that this was really nice. He says to me, so method of washers is like filling up the region with slices from left to right or from bottom to top. But when you cross-section using cylinders, you're filling up the region using slices from inside to outside, kind of like an onion. So that is what we're doing here. Lots of food analogies today. Now, the area of a cylinder is 2 pi times the height of the cylinder times the radius, 2 pi hr or 2 pi rh. The radius of the cylinder is the distance between the center of the cylinder and the edge, so that would be r. But notice in this drawing, the distance between the center and the cylinder and the edge is exactly the same as this arbitrary x value at which we have taken our slice. The radius of the cylinder, r, is equal to the x value at which the slice is located. R equals x. R equals x. So now, let's go ahead and try and figure out what h would be. What is the height of this cylinder? Now, look at this drawing. The height of the cylinder goes between a lowest point, which is located on the blue graph, and a highest point, which is located on the green graph. The height of the cylinder is the difference between those two output values. The height of the cylinder is the difference between the upper output value of 2, given by the upper function g of x, the difference between that and the lower value given by the bottom function f of x. The height is g of x, top function, minus f of x, bottom function, and the radius is x itself. So that means that the surface area of some arbitrary cylindrical cross-section is given by 2 pi times x times 2 minus x minus 1 squared plus 1. This is given by 2 pi x g of x minus f of x, top minus bottom. And so, to find the volume of this region, all that I would have to do is integrate from the leftmost slice to the rightmost slice this area function. Now, once again, I implore you not to just go through and try and memorize formulas, because this formula in particular is very easy to get mixed up with the method of Washer's formula that we did in the previous section. But always, 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 every single time, get a drawing going, draw one of your cross sections, and then, based on that drawing of a cross section that you found, set up an integral that reasonably matches your drawing.